Welcome back, everyone, to the Algebraic Graph Theory Seminar. This week, we have Whitney Drazen from Northeastern University, who's going to be telling us about fractional revival and approximate fractional revival on path graphs. So I will let Whitney take it away. And you will need to
unmute myself. Okay, there we go. Can everyone hear me? Or someone hear me? Okay, all right. So thank you for having me here to speak at the Algebraic Graph Theory Seminar. I've enjoyed attending the talks. Now that it's virtual, I'm able to do so. So that's has been a nice thing. All right, so today I'm going to talk about generalized fractional revival and approximate fractional revival on the path graph. So we've had some talks before about fractional revival on two nodes, and this is going to extend that notion to larger sets of nodes. So it's going to be similar to things we've seen before, but it gets a little bit more delicate when you have larger sets of nodes. As an aside, I'm graduating this year, so if you have a postdoc position lying around that you're not using for next year, I'd appreciate your consideration. Okay. So what are we going to talk about today specifically? Well, we're going to talk about these notions of generalized fractional revival and generalized approximate fractional revival. So the extension of these two node phenomena to larger sets of nodes. We'll go through some definitions, examples, and a spectral characterization. So this first part is joint work with Ada, Gabriel, or Eisenberg, Chris Godsell, Mark Kempton, my advisor, Gabor Lipner, Tino, and Harmony. And then part of the approximate fractional revival stuff is joint work with Ada, or Eisenberg, Gabor, and Mark. So the second part, we're gonna focus on the path and say, and specifically apply these to the path graph and construct some families of sets of vertices on the path graph that have approximate fractional revival. And the second part of the talk is joint work with Ryan Coletti, Gabor Lipner, and Noble Mushtaq. Ryan Coletti and Noble Mushtaq are two RU students that I was supervising this summer. Okay, so let's get into the first part, just the basics about generalized fractional revival and approximate fractional revival. So I know we've all been through this before, but is that okay? All right. But we want to talk about continuous time quantum walks. So what exactly is a continuous time quantum walk? Well, it's a process on a network of quantum particles whose connections have a graph structure. So the transition matrix of this process is given by the exponentiation, so e to the ITM times the adjacency matrix of the network. So this means that for initial state x0, our state at time t is given by u of t times x0. Okay, so what's the relationship between m and u of t? Well, by the spectral theorem of symmetric matrices, as you've seen before, we can decompose m into the sum of its real eigenvalues times its idempotence. And then u of t keeps these idempotents. So sort of the spaces it acts on are the same, but the difference is that the eigenvalues are multiplied by a time parameter and exponentiated. So u of t is unitary and symmetric, and it has an inverse that's just given by going backwards in time by t instead of forwards in time. Okay, So as kind of a couple examples, we have M1. So the particular entries of this matrix aren't important. What's important to note is that it has this M1 gives you the structure of U of t, which is e to the it m1. So in this case, our first idempotent acts on a two-dimensional space, and our second idempotent acts on a one-dimensional space. And the eigenvalues are given by the exponentiation. So we have our first eigenvalue is -1 in M1. So that eigenvalue in e to the it m1 is e to the it -1. And the second eigenvalue is 2. So that eigenvalue turns into e to the it e to the it times 2. So in terms of how we think of this evolving in time, what happens is that we maintain throughout the time evolution those same fixed spaces, but what happens is that our eigenvalues wind around the unit circle. So hopefully you can hopefully that animation is coming through okay. But what all we're all that happens is that these eigenvalues are winding around the unit circle, and the rate at which they're winding around the unit circle is given is proportional, I should say, to the eigenvalue of m. Okay, so here's yet another example. I'll sort of fast forward through this, and here we can see another time evolution of our eigenvalues, again, winding around the unit circle. Now you'll notice that the third eigenvalue didn't move at all, and that's because the eigenvalue coming from m was 0, so e to the it times 0 is e to the 0, which is just 1. Okay. All right, so now that we've explained a little bit more about what the relationship is between the process U of t and our original adjacency matrix M, we can give a definition of fractional revival. So in this definition of fractional revival, the generalized fractional revival comes from that first joint paper I was talking about. So we say that M admits generalized fractional revival if at time t among the columns indexed by k, so k is some subset of our vertices, and that it admits generalized fractional revival if U of t has a block diagonal structure up to permuting that should say permuting rather than permuting the rows and columns. So we have our upper left block corresponds to the k by k columns, and that that entry is H, and then we have a lower right block corresponding to the complement of k, and the cross entries are 0. And again, this U of t, since U of t is symmetric and unitary by the block form decomposition, so is H, and also so is U prime of t on the bottom right. So the relationship to perfect state transfer is that if we prescribe that H is alpha times this anti-diagonal 2 by 2 matrix, then this is exactly equivalent to the definition of perfect state transfer. Okay, so let's just look at some examples of graphs that have fractional revival, or actually a couple constructions and then some graphs. So if we have a graph X that is periodic at time t at a vertex A, and then we have some other graph Y that has a non-diagonal transition matrix at that same time t, then we get fractional revival at time t on A times the vertices of Y in the Cartesian product of x and y. We can also join a k regular graph and an h regular graph. So by joining, we mean taking two separate graphs, and then you connect each vertex in x to every vertex in y, and keep the connection set within x and y the same. So if we take that, then we get fractional revival on the vertices in x. And some examples of two-vertex fractional revival that you may have seen before, which come from a 2018 paper by Ada, Gabriel, Tino, Luc Vinet, and Harmony, are the cycle on 4 vertices and the cycle on 6 vertices, which it turns out are the only cycles that have two-vertex fractional revival. And then we also have this K16 Cartesian product with K2, and it has, and all of these lower examples with the pictures have fractional revival on the two vertices that are white. Okay, so with the definition of fractional revival, we can also define approximate fractional revival. So approximate fractional revival, we have the same indexing of vertices in K. And then we say that we have pretty good fractional revival if up to permuting the rows and columns, we get that for all epsilon greater than 0, there's a time dependent upon that epsilon, such that u of t at that t sub epsilon has a block form as seen on the screen, and where the norm of each of the rows in the off diagonal blocks goes to 0. So basically, it gets close. It gets arbitrarily close to that block diagonal form that we saw in our definition for fractional revival. And so we'll see that fractional revival and approximate fractional revival both have some similar spectral characterizations. Okay, so one of the first necessary conditions on fractional revival is that the restrictions of our idempotents commute with H. So that's the upper left-hand block. So that's indexed by the vertices in K. So if we have u of t, if we define u of t in the block form, and we also defined E sub j, so some idempotent in a block form, and then we have that u of t and E sub j both commute with each other, since they're both linear combinations of the idempotents. And so if we restrict our attention to the upper left-hand corner of our matrix of ut ej and ej ut, then we can see that we get what's down on the bottom, which is that h times the restriction to the k components of E sub j is equal to the restriction of E sub j to the k components times h. And this is valid for all j. So a similar computation will show that this is also a necessary condition, so that in the case of approximate fractional revival, basically all you have to do is specify that there exists such an H that that these ut sub epsilon converge to in the block form, and then basically the computation is the same. Okay, so this is important that that the restrictions of the idempotent and this H matrix commute. Okay, so what's the connection to cospectrality, which is a necessary condition for perfect state transfer? Well, if we prescribe that our H matrix is this this anti-diagonal matrix, and that the idempotents commute with this H, then we just sorry, all of these, I know it's a typo, all of these E's should be indexed by J. So basically, after you do the multiplication, the diagonal entries are both E sub J UV, and the off diagonal entries are either EJUU or EJVV. And so since those two matrices are equal, we know that the EJ component, or the UU component of EJ and the VV component of EJ are the same. And this is one of the characterizations of cospectrality. Okay, so fractional cospectrality has, similar to regular cospectrality, has a lot of different characterizations. So if we define that M is the matrix that our adjacency matrix, and K is the subset that we want to be fractionally cospectral, and we prescribe that H is a unitary matrix that has the same size as our cospectral set. Then this H matrix will have some spectral idempotents, and we can characterize fractional cospectrality either by the inner product of the eigenvectors corresponding to H being 0 when projected onto ER, or that the idempotents or that the idempotents of H are 0 when we have a projection onto the restricted idempotents in the middle. But the two most important characterizations are the last two for the purposes of this talk, and that's that there's an H commuting with the restriction of the idempotent, or that there's an H commuting with the restrictions of the powers of the adjacency matrix. So these are going to be the characterizations that we use to define the fractionally cospectral sets on the path graph, and eventually figure out which ones have approximate fractional revival. Okay, so there's another important property called strong fractional cospectrality, which instead of having that H just commutes with these restrictions of E sub J, says that in fact these E sub J lie in a specific, these E sub J's project, these restrictions of our idempotence E sub J actually project onto an eigenspace of this matrix H. So if this happens, then we say that that the set K is fractionally cospectral. And this you can certainly see just by just by taking the transpose of H restriction of E sub j, that this is indeed a stronger condition than H commuting with E sub j. Okay, and if we combine this condition with the condition on our eigenvalues, then this will characterize fractional revival and approximate fractional revival. All right, so what exactly is the condition on the eigenvalues? The condition on the eigenvalues is going to say that we need projections that we need restrictions that project to the same eigenspace of H to have the same eigenvalue. So, so if we just take, let's see. So if we just take the form that we get in fractional revival, and we look at the upper left-hand block, we get the following equation. And then by strong fractional cospectrality, we can rewrite it as that equation as follows. And then so that tells us that the restriction of EJ times EI is equal to these constant multiples that came from strong fractional cospectrality. And so this is going to give us that this alpha j times alpha I inverse is equal to 1, or that our projections are orthogonal. So basically, if we apply this to the matrix coming from fractional revival, then our alphas are necessarily e to the it lambda j and e to the negative it lambda I, and so those multiplied together must be equal to 1. And rearranged in this form, it's going to give us a little bit more about the dependence of lambda j and lambda I. Okay, so what is this condition on the eigenvalues really? Well, graphically it says that if we have some eigenvalues, we're then going to group our eigenvalues depending upon whether they're orthogonal or not. We're going to group our eigenvalues depending upon whether the restricted idempotents are orthogonal or not. And then once we group those eigenvalues, we need the eigenvalues in those groups to correspond at some time t. So graphically, what that means is that as these eigenvalues are rotating around the unit circle, we're going to get fractional revival if and only if these groups, the eigenvalues in these groups align. So you can see here they all stopped at all of the eigenvalues in the group stopped at the same place. What that means is that all of the eigenvalues in that group are aligning at the time at which we stopped, at the time at which we're observing. And so that means the eigenvalues are coincident, and hence we have fractional revival at this time. So we have to group the eigenvalues and see if there's a time at which all of the eigenvalues in each group simultaneously overlap with each other. Okay, and so those are the conditions for fractional revival, and approximate fractional revival is going to have a very similar characterization. So instead of our eigenvalues needing to line up precisely, we need to get that our eigenvalues can come arbitrarily close to lining up precisely. So that can mean one of two things. That can mean either that they do in fact line up exactly as we want them to, or that can mean that no um, there's no relation between the eigenvalues that would prevent them from lining up in some sort of arbitrary configuration. And so that's exactly what this theorem says. So we get that there's pretty good fractional revival among the vertices in K if and only if we have that the vertices are fractionally cospectral, and that we have this condition on linear combinations of them, that if we have a linear combination such that we look at one group of our eigenvalues that need to line up coming from our strong fractional cospectrality, and we look at the rest, and this linear combination sums to 0 with all of the coefficients summing to 0, that this implies that that the sum over that first group of eigenvalues is not equal to plus or minus 1. So this the proof of this isn't too complicated, but a little bit longer than is suitable for a talk. But basically, this just says we can get arbitrary configurations of our eigenvalues with respect to the different groups. Okay, so let's see how this all applies to the path graph. Okay, so you'll recall we had these characterizations of fractional cospectrality, and the characterization that's going to be most important here is that we have some H that commutes with the restriction of the powers of our adjacency matrix for all K. Okay, so as is common knowledge, m to the k represents combinatorially walks on our graph. So m to the ijth entry of m to the k is the number of walks of length k from I to j. So we need h to commute with all restrictions of this matrix that's defined combinatorially by the walks on our graph. So we need this for all k, but really we only need to look at k from 0 to n minus 1, and that's because we can have at most n linearly independent terms in our set of restrictions of m to the k. And this is because we have only at most m idempotents, and all of these m to the k are linear combinations of these idempotents. Okay, so to analyze the combinatorics of walks on the path, first we're going to look at walks on a one-dimensional lattice. So a walk a walk from a vertex J is just a series of plus and minus 1 moves. We can either go to the right or we can go to the left. We don't have too many choices for our walks. And so if we say that D is the difference between the number of +1 moves and the number of -1 moves, then our endpoint is j plus d. And so how many ways can we get a walk of length k from j to j plus d? Well, this is simply the binomial coefficient, where we're choosing k, where we're choosing k plus d over two things, where we're choosing k plus d over two things from k things. So the k plus d over 2 comes from the fact that if you choose k plus d over two things, then you've chosen d more +1s than you have -1s. So we're choosing the +1s and the remainder of the -1s. So, and if k plus d is odd, then we're just saying that this this binomial coefficient is 0, because there's no way to choose a half a thing. Okay, so for ease of notation, we're just going to call this nkd. So we don't have to keep writing out the more complicated binomial coefficient. Okay, so we can look at, right, so we can look at walks on the one-dimensional lattice, and that'll give us an overestimate of the number of walks total, because the number of walks total, some of them at like this one will leave the vertices that are in the path. So that means if we just take a binomial coefficient, then we're certainly overcounting. So how do we correct for that overcounting, or how do we quantify what that overcounting is? Well, we can we just find a correspondence between walks on between these overcounted walks and some other walk on the one-dimensional lattice here. So we have so we can have a walk that mirrors the bad walk, so the walk leaving the path. And then when we leave the path, we instead mirror the walk leaving the path and returning. We mirror that and count that one we mirrored. So basically we wait till we arrive at the vertex 0 for the first time. If we're leaving the path from the left side, we're going to reach the vertex 0 at some point. And then after that point we reach 0, we reverse the steps we take. So that's indicated here by the red arrows. And as you can see, in the original walk, we ended up at 1, and the mirrored walk or reflected walk, we ended up at -1. And that's not a coincidence. So the however many steps the red arrows go, either to the left or the right, since we reversed the upper red arrows on the bottom to get the lower red arrows, we're going to go the opposite way, so the same distance, but the opposite way from 0. So so in the upper path, we went from 0 to 1, and in the lower path, we end up going from 0 to -1. Okay, so this is we're going to use the same general principle to count these walks. So for each k, the reflected walks are in bijection. So the reflected walks from, so that is the walks from j to negative I, are in bijection with the walks leaving the path that go from j to I. And that's simply because every walk that reaches negative I has to go through the vertex 0, and we have basically all the freedom we need to choose these plus or minus ones. We have all the freedom we need to choose the plus or minus ones to arrive at negative I. So we can call this number of walks from j to negative I, we can simply think of as n sub k j plus I. So it's the number. So recall that means the number of ways we can have a path of length k that moves j plus I spaces from its starting point. Okay, so let's also note that the argument in n sub k is the length of the shortest walk from j to I that leaves the path. So if we go from j to 0 and then 0 and then back to I, that's length j plus I. Okay, so we can do the same trick on the right endpoint. And it's basically it's the same thing, only we're looking at reflecting paths about n plus 1 rather than, because that's the first vertex outside of the path. So we're looking at reflecting walks about n plus 1 rather than reflecting walks about 0. And so it's the same thing. We still our endpoint our endpoints are equidistant from n. The reflected endpoint and the original endpoint are equidistant from n plus 1. And we can count them in exactly the same way. Okay, so we can make a similar argument. Okay, so all right, so we made that similar argument for our vertices close to n. And so, okay, so now we have a correction factor for walks. We simply take we have so we know that the ijth entry of m to the k is n k. So this binomial coefficient corresponding to moving I minus j from the starting point. And then we have to have a correction factor, and that correction factor is depends on k and the length of the shortest walk from I to j leaving the path. And that's, it turns out to be enough to get the ijth entries for k up to n minus 1. Okay, and that's because, as it says, walks of length n minus 1 are shorter from I to j can only leave the path on one side. So if we have a walk from I to n minus I, then that leaves the path on the left side, goes to the 0 vertex, then this then the length of the shortest path leaving leaving the path from I to n minus I is is length n, which we don't care about because it exceeds n minus 1. So that means that if we go from I to if we want to know what the paths are leaving the what the walks are leaving the path from I to another vertex, then if our other vertex is n minus I minus 1 or less, then we can leave the path from the left side. But if we if our other vertex is greater than that, then we cannot leave the path from the left side, because that the shortest path leaving the shortest walk leaving the path from the left side is of length greater than n. Okay, so let's look at a 3-vertex evenly spaced example, and we'll see how we might construct how we might use this combinatorics to find fractional cospectrality. So we have a formula for all of the entries of m to the k. So it's the distance between I and j. So it's a binomial coefficient based on the distance between I and j, and it's another binomial coefficient that we subtract out that's based on the shortest path between I and j that leaves the path, or sorry, the shortest walk that leaves the path. So since we have this formula, we would, and we know that we need to find, we know that for fractional cospectrality, we need to find a matrix that commutes with all of our restricted restrictions, all the restrictions of m to the k for all k. Then we would have to check these. We would have to check up to n different restrictions. But there's a shorter method to do this. So we can generalize that example that I had before and replace the vertices with something that with a variable that indicates the relationship between the distances. So here we have vertices a, 3a, and 5a, and a path of length 7a minus 1. And we just want to construct these, we just want to construct the restricted powers, the powers of the restricted adjacency matrix. So, so let's recall that we need this vertex 0 and this vertex 7a, because these tell us how, these are the vertices that we need to go through to make a walk leaving the path. And we can fill in this restricted power of the adjacency matrix. So in our first entry, we have nk of 0 minus nk of 2a, and that's because 2a is the shortest path from the vertex a to itself, or the shortest walk from a to itself leaving the path. Down the bottom right, we have nk0 because the shortest path from 5a to 5a is length 0, and the shortest walk leaving the path from 5a to itself goes from 5a here to 7a and then back to 5a. So that's of length 4a. So we need to subtract something that depends on that length. And we can do the same thing for our other entries. So between A and 3A, the distance is 2A. So the total number of walks on the lattice would be something depending upon 2A, but the walks that leave the path is this binomial coefficient that depends on 4A, since the shortest walk leaving the path from 3A, from A to 3A goes first to 0 and then to 3A, so that's length 4A, and we can fill in the rest of this matrix in a similar way. So what you'll notice is that there are a lot of entries in common. So what we can do is we can factor out those entries and decompose this matrix into a sum of 4 other matrices. And so so this decomposition is true for all K. So what this means is that if we can find a matrix that commutes with these 0, 1 matrices, then since m to the k is just a linear combination of these 0, 1 matrices, then the matrix that commutes with these 0, 1 matrices will also commute with m to the k. So is there such a matrix? Yes, and in fact, they commute with each other. Okay, so we can generalize this process, and we can just define these matrices B sub k, where basically B sub k is equal. All right, so basically B sub k is equal, B sub k ij is equal to 1. This should say if the distance all right, so this should say distance between I and j is k. So if the distance between them is k, then we're going to have a 1 entry. And if the distance between, and if the shortest path leaving, sorry, the shortest walk leaving the path between I and j is k, is length k, then we're going to get a -1. So we're going to get these +1s for the binomial for the general walks on the lattice, these -1s, and these B sub k's if k is the length of a correction factor. And it turns out that these m's that the powers of m to the k actually span these B sub k matrices. So what that means is that since we have these B sub k span the restricted powers of m sub k, it means that something commutes with B sub k if and only if they commute with the m sub k. So really, finding a matrix that commutes with the 0, 1 matrix won't just tell us that there exists one, but if we can't find one, that means that there doesn't exist anything that commutes with these with the restricted powers. Okay, so in the interest of time, I'll skip ahead a little bit. So we want to to determine if there exists a matrix commuting with the restricted powers of the adjacency matrix, we can instead of looking at the powers of the adjacency matrix, we can look at some simpler -1, 0, 1 matrices that are heavily dependent upon the structure of the vertices we've chosen in the path. And so to check if there is this commuting matrix, we find some m sub j, or in this case a b sub j, the 0, 1 matrix that has a 1-dimensional eigenspace. This is going to be relatively easy to do because these the 0, 1 matrices are sparse. And then we check and then corresponding to that eigenspace, we have an eigenvector, and we find the span of that eigenvector under the m to the k. And then the span of this is the smallest possible eigenspace containing this phi that commutes with h. Okay, and so if the dimension of this span is less than the size of k, then we've basically constructed a commuting matrix. It's just something that has one eigenvalue on the idempotent for the span and something else for its orthogonal complement. Otherwise, if the span is equal to k, then we've shown that no such commuting matrix exists. Okay, so why would we want to separate into these 0, 1 matrices? Basically because it greatly simplifies the cases we have to look at for size of k equals 2. All of the sets, all of the ways we can select two vertices in a path are characterized by a set of these 0, 1 matrices that come from these 4 examples. And if we want to check what the fractionally cospectral sets of vertices of size 3 on any path are, then really we can check some 0, 1, -1 matrices, see if there's a matrix that commutes with them, and that's really there are only about 30 of them up to size if we have our size 3 as the size of our fractionally cospectral set. Okay. So let's go into some families of examples. One family of examples is where we have A, 3A, 5A, so all odd multiples of A are the vertices, and we have some 2K plus 1 times A minus 1 vertices total. Then this is a family of fractionally cospectral example. This is a family of examples of fractionally cospectral sets. It can be shown, though it's a little bit tedious, that in this set the restricted powers of m to the k commute. Another example is something where we have an alternating spaced asymmetric example. So here our vertices are A plus 2B, 3A plus 2B, and we have a length of 3A plus 3B minus 1. So we can show that we can show that 1 minus 1, 1 is an eigenvector of the restriction of m to the k for all k. And furthermore, if we have two such examples on the same length path, we can overlay these examples, and now the 6 vertices together will also be a fractionally cospectral set. So if we just take every single combination where A and B sum to the same number, then we can almost tile the path. We're only missing A and A plus B and 2A plus 2B. So we can extend this example by having arbitrarily many vertices. You just repeat the pattern. The distance between one vertex is 2B. The distance between the following vertex is 2A, 2B, 2A, 2B, 2A, etc. And the eigenvector for this example will have alternating plus and minus ones. Okay, so then we can have a symmetric example that has the same character. The spacing is 2B and 2A with a spacing of A minus 1 on the left-hand side and a spacing of B minus 1 on the right-hand side. And we can also extend this by having alternating 2A's and 2B's. And we can also overlay different examples as in the asymmetric case with these 2A's and 2B's. Okay, so are these all examples of fractional cosplay?
So if you could find a stopping place, that'd be great.
Yeah, I'm gonna stop in 1 minute.
Great, thanks.
Okay, so are these all examples of fractional cospectrality on the path? Up to so I don't have a general technique to prove this quite yet. Up to K, size of K is 8. These are all the examples. If K is greater than 8, I don't know. Which of these actually achieve pretty good fractional revival? We can characterize this by in the following way. In these type 1 examples, we have pretty good fractional revival if and only if A is a power of 2 and K is prime. So where K is given basically K is given as follows. It's the number of vertices we have in the set. And in these alternating space where we have 2A and 2B vertices separated by 2A and 2B, then these are both characterized the same way. We have approximate fractional revival if and only if K is prime and A plus B is a power of 2. Okay, and I won't go into the proof of this, but it just deals with the fact that cosines can be decomposed into roots of unity, and then we use the theorem we had about the linear combinations of eigenvalues to prove that there is or isn't fractional cospectrality. Okay, all right, so I will end there. Thank you, everyone, for listening, and I hope you got something out of the talk. I'm happy to answer some questions either now or in a smaller session later.
Thank you very much.
Thank you.
Let's thank Whitney. So yeah, as Whitney said, let's see if we have any questions for right now. I can start with one. I'm just wondering if this technique that you're describing, where you sort of like you're putting your path inside a larger path and correcting for walk counts. I'm wondering if you think there's other classes of graph that this might be applicable to in order to get sort of counts on powers of the adjacency matrices in nice ways.
Yeah. So really, what's let me say something maybe not exactly this, but a little bit different. So this thing where we can decompose our adjacency matrix into this like 0, 1, -1 is sort of basically it's dependent upon the fact that the number of walks is between two vertices is dependent upon the distance between them. So anytime you have a structure like that, you could apply similar reasoning to it. But you'd need to have sort of it needs to be very regular. You're going to have, I think, a lot of automorphisms of your graph if you want to apply similar reasoning.
Right. Makes sense.